All right, so we're talking about limits today. It is the basis of calculus. By the end of the period, you'll be able to understand what a limit is, what convergence is, and how to use limit notation, because limits is the foundation, okay? It's the basis of what everything else in calculus is based off of, okay? So, this right here, this is your notation for a limit, okay? It does include the LIM, that stands for limit, okay? There's always some type of variable that's approaching a number or infinity, okay? So we have the limit as n approaches infinity for this particular example. And then we have u sub n. In this particular case, u sub n represents a sequence, okay? Like a series of numbers, okay? That follow a particular pattern, and it equals L. Okay? That is how that notation is read. L is the number that the sequence approaches as n approaches infinity. Okay? So when we think of a sequence, okay, that's a series of numbers, such as 8, 4, 2, 1, 1 half, 1 fourth, 1 eighth, so on and so on. Can you identify what the pattern is? We're dividing by 2, or what's another way to represent that? Or multiply by 1 half, okay? So u sub n represents a sequence. Let's pretend that this is u sub n, okay? The limit as n approaches infinity. Now n is representing the number of terms that are in the sequence, okay? Because clearly the dot 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 means what? What's dot 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 mean? It keeps going, okay? So then it'll be like 1/16, 1/32, so on and so forth, okay? So as n continues, as n approaches infinity, because we can have a series of number of terms, this limit is approaching what number? It's approaching 0, because the bigger or the further along we get in the sequence, the bigger the denominator gets, but the numerator is still staying 1. Okay? So in this case, we would write, say this was, what's the limit of this sequence, we would write it as such. The limit as n approaches infinity of the sequence would equal 0. Because that's exactly what's happening. As the sequence continues, the number is getting closer to 0. Okay, that's what the limit is. You're looking to see, okay, what's happening? The more numbers we add, what's happening? What's happening to the numbers themselves? Now, a limit converges if the sequence approaches a specific number, such as this. Okay, the example that I gave you, that is a limit that is converging because it's approaching a specific number. Yes, it's 0. 0 is still considered a number. However, a limit diverges, and I know I misspelled that, but a limit diverges if it does not approach a specific number, okay? So let's say that it approaches infinity. Infinity is not a specific number. So the sequence is, continuing to get bigger. It's never going to approach a particular number, is it? No. Or if it oscillates in between two numbers. Does everybody know what oscillate means? What does it mean? Like going back and forth between two numbers. Okay, like going back between two numbers. All right? So let's look at some examples. We're going to determine if each sequence is convergent or divergent. And if a sequence is convergent, we're going to give the limit of that sequence, because we can only give limits of sequences that do indeed converge. Okay, let's look at the first one. We have 0.3, 0.33, 0.333, 0.3333, and so on and so forth. Would you say that this sequence is convergent or divergent? Say again. It is convergent, okay? Because if you continue this pattern, you'll get, 0.33333, 0.33333, 0.33333, and as we know, if we continue to add 3's forever, that technically is going towards what number? No, not 0. Not 3. Not 0.2. What's 0.3 repeating? 1/3. Okay, because right now we have, 30%. Okay, so 0.3. Then we have 0.33. Okay, but no matter what, as you continue to add 3's, you are going to have 3 that doesn't end. Okay, 0.3 forever. And that's exactly what the decimal approximation is of 1/3. So we'll have the limit as n approaches infinity of this particular sequence equals 1/3. Questions? So think of like a limit is, okay, what number are we getting close to? If we're even getting close to a number at all. Okay? What about B? Is that convergent or divergent? Well, if you say convergent, you got to tell me what number are we getting close to. If it's divergent, you need to explain why. So which one? Why is it divergent? It's not going to a specific number. These numbers are actually doing what? You're multiplying by 2, so they're actually getting bigger. So it's going to continue to get closer to infinity. So this one is divergent. Okay? Questions up to here? Alright, I want you guys to do C and D. C and D. If you want to use your calculator for C, that's fine, you can. You are going to need it later, so you will need to get it out at some point. Was C convergent or divergent? It was convergent. And what is the limit? It's approaching what number? Well, in order to be convergent, it has to be approaching a number. What number? It is 1/4. It is 1/4. Okay? Because you have 1/5, which was 0.2. And then 6/25 was what? It was 0.24. And then 31/125 was 0.248. And then 156/625 was 0.2496. And then the next big number was 0.24992. Okay? If you were to continue this out, you would see that this number is going to get close to 0.25, which is 1/4. What about D? This is divergent. It goes back and forth between 1 and -1. What other thing do we know that goes back and forth between 1 and -1? Sine and cosine. More specifically, what about sine and cosine goes back and forth between -1? The y values, aka the, thought I heard it, the range. Yes. Now, with functions, it works the same way, okay? Except this time we're looking at actual graphs. We're looking at graphs of sines or cosines, exponential functions, quadratics, etc., etc. So when we're looking at functions, we're still trying to determine what is the limit, but this time we're looking as x approaches a particular number, that's what C represents, from either side of the function. That means looking at it coming from the left-hand side and then also coming from the right-hand side. And L is actually the y value. Okay? So as x approaches a particular value, 2, -1, whatever, it should be approaching one number from the left-hand side and the right-hand side, and that number should be the same. The number you're looking for is exactly the y value. Okay? Now, if you do examine the graph, and you see that, hey, from the left-hand side it approaches one number, but from the right-hand side it approaches a completely different number, then in those cases the limit does not exist. Okay? Now, it really is not as bad as it sounds, or as I'm explaining. It's actually very simple, but the thing is, you're looking at what's happening to the y's the closer you get to these x values. That's really what it is. Okay? So let's look at some examples. You'll need your calculator for this. All right? We're going to find the limit or state that the limit does not exist. Okay? So we have the limit as x approaches 2 of x squared. So we're going to turn on our calculator. We're going to go to our y equals. And we're going to type in x squared. I want to go back to my standard window because who knows who had your calculator or what you did last time in your calculator. So Zoom 6 always takes you back to a standard window. And there is our quadratic. We already knew that's what it looked like, yeah? Okay. So now, it says the limit as x approaches 2. Okay, so as we get closer to 2 along the x-axis, what y value is it approaching? Okay? So as x gets close to 2 from the left-hand side, and as x gets close to 2 from the right-hand side, What number does it look like it's approaching? 3 or 4? Using the graph is actually kind of hard to see, especially when it's like, on this tiny little, 2x2 screen that we're looking at. So let's go and let's look at our table. Okay, our table can actually give us a better idea of what's happening the closer we get to 2. Before we go look at our table, let's fix the setting. So go to second window. Second window is table setup. This is how you can basically look at the different X values on your table. Clearly, we're concerned about what's happening around 2, so we'll start at 2. And this triangle TBL basically means the change of your table. How do you want it to increase? Normally, our table goes by ones, okay? 2, 3, 4, 5, 6, whatever. But we're trying to see the closer we get to 2. So let's open it up. We can do 0.001, or if you want to do, let's do 0.01, okay? And now when we go to second graph to actually look at our table, what we'll see is actually what's happening as X approaches 2 from the right-hand side. Because if you think about it, coming from the right-hand side, we're coming from 5 to 4 to 3 to 2.5 to 2.4 to 2.3 to 2.2 to 2.1. What's happening to those Y values? They're approaching 4. Let's check from the left-hand side. That's coming from 0 and 1 and 1.5, 1.6, 1.7, 1.8, 1.9. What's happening to the Y values the closer we get to 2 from the left-hand side? It's approaching 4. So we know that the limit is equal to 4. Will they always be this simple? Of course not. But I'm starting you off with the most basic example, so that way you can kind of have a grasp on it by the time we get to the more challenging examples. Yes? Here we go. Okay? Let's do B. The limit as X approaches 1. Now we're using our calculator, and we got to let our calculator know that we want X squared minus 1 being divided by X minus 1. So what do we want to make sure that we do? Parentheses, exactly. So let's type B in, and let's see what we're approaching. Before you go back to your table, what's the X value that we're approaching? Approaching 1. Before we were closer to 2, and we have our table setting by 0.01, so it might take us a while to try to scroll up there. So let's go back to our table setting, and let's start at 1. Because right now, you see where I was at 1.94, so it's going to take me a while to get closer to 1. So on my table, I'm not concerned what's happening at 1, I'm concerned about what's happening the closer we get to 1. So from the right-hand side, what number is it approaching? It's approaching 2. Let's check the other side, because they have to be the same. If they're not the same, the limit does not exist. Coming from the left-hand side, what number are we approaching? 2. So our limit is 2. Questions? This one. The limit as X approaches 0 of the function. What kind of function is this? It's a piecewise function. And you know that you can't really graph a true piecewise function in the calculator, so you're going to have to go and do this one by hand. Okay? If you want to at least look at the graph. Okay? Now we have f of x equals 1 for all the x values that are greater than or equal to 0, and f of x equals negative 1 for all of the x values that are less than 0. Now f of x equals 1 is the same thing as saying y equals 1, and f of x equals negative 1 is basically the same thing as saying y equals negative 1. What do those two graphs look like? What does y equal 1 look like? Horizontal line crossing through the y-axis at 1. So it's crossing through the y-axis at 1, but we only want the part of the horizontal line that's for all the x values that are greater than or equal to 0. So we're starting at 0 with a closed circle because it is equal to 0 here, and it's everything that's greater than 0. For y equals negative 1, that's another horizontal line, but this time we're crossing the y-axis at negative 1, and what's happening at 0? Is it defined? No, so we're going to do an open circle there and draw it going this way. approaches 0, from the right-hand side, what are my y's approaching? 1. From the left-hand side, what are my y's approaching? -1. Since they're not the same, what's the limit? Does not exist. Questions? So we're trying to basically looking at what happens the closer we get to a particular value. 0 was in this case. Let's look at a different type of piecewise function. Let's look at this one. We have the limit as x approaches 2 of x squared plus 3 and -x minus 2. What do both of those graphs look like? They're linear functions, yep. So they're going to be lines, horizontal, vertical. They are diagonal. Let's get a little bit more specific. I'm trying to get you there, okay? Come on. How would I graph x plus 3? Start at 3 on the y-axis and
go up 1
up 1 over
over 1.
1. And then?
Up 1 over 1.
And continue all the way through. And there we'll make our line, but I don't want the full line for x plus 3. I want all the values for x is greater than or equal to 2. So I go to 2. That's this point right here. Is this an open circle or a closed circle right here? And it's everything that's greater than 2, so that's all of these values over here. You graph piecewise functions back in algebra 2. Maybe in pre-cal, I don't remember. Here we go, -x minus 2. Where do I start? -2, and then I do what?
Go down 1 over 1.
We go up 1 and to the left, up 1 and to the left, or we could go
Down 1 to the right.
down 1 to the right 1, down 1 to the right 1, down 1 to the right 1. But for this one, I want only the x values that are less than 2. So I go to 2, open circle or closed circle? Open, and it's everything less than, so it's all of these values going this way. You can see from this piecewise function that the limit from the right is approaching what number? As we approach 2 from the right, it's getting closer to what number?
Oh, you mean the y.
It's always the y values, because the limit as x approaches 2 will tell you what x value you should be getting close to, but the actual limit itself is the y value. What about from the left-hand side? What number is it approaching? What is it?
Excuse me, Miss Anderson?
Yes.
Back.
What number is it approaching? -4. Are they the same? So the limit does not exist. Now before you think, oh, so all piecewise functions are not going to exist? No, that's not the case. It really just depends on what is given to you in the piecewise function. So you always want to make sure you want to double check, okay? All right. I want you to do the next one on your own. You are going to have to use your calculator. I'll check back in with you in about 2 minutes. All right, so for this one, the limit as x approaches 0 of sine x over x. What you guys get? It was equal to 1. Hopefully you were in radian mode, because I think the graph kind of looked like this a little bit. And we're looking, it was approaching the same number from both directions, which was indeed 1. Okay? Questions on doing it graphically? All right? So for SL, you're more expected to be able to apply some algebraic manipulation or to evaluate the limit of functions, okay? So we're going to take a look at some of these algebraically. And technically all, well, not all of them. Well, actually, it's all functions really can be found, the limit can be found algebraically. Some are pretty simple, they involve just a little bit of manipulation, okay? Some of them are even easier where literally you just plug in and figure it out. Some of them you have to report back to former concepts. And then some you actually have to use more advanced concepts. Okay? But if you look at A, this is the limit as x approaches infinity of f of 5x minus 3 all over x. Now before we even get into figuring this out algebraically, what type of function is that? 5x minus 3 over x, what type of function is that? It's a function that we have talked about. It is not linear, that's true. Huh? It is a rational function, yes. Now, do you guys remember what rational functions look like? Rational functions have the two branches that look like this, right? And if you think about it, right, whenever x approaches infinity, okay, you basically were looking at what happened to the graph the bigger that x got, right? And didn't every rational function we dealt with this year level out to a particular number? What did that number represent? The type, the horizontal asymptote. So, if you ever have to evaluate the limit as x approaches infinity of a rational function, it's basically asking you to find the horizontal asymptote, which is just 5. Using your knowledge of rational functions that when the denominator and numerator are equal, you look at the coefficients. Now, if I wanted to do it out algebraically, which is still doable, you can split up the numerator to be 5x over x minus 3 over x, yes? Doesn't 5x over x simplify? To what? 5. 3 over x does not simplify. And if you really think about it, if you plug in a super, super big number in for x, 3 over a super, super big number is what? A super, super small number, almost like what? Close to what number? 0. So the bigger that x is, the smaller that this is going to get, meaning that it's going to get closer and closer to 0. What's 5 minus 0? There you go. Okay. B is a pretty simple one. Now we do have two different variables, which means that our limit is not going to be one set number. It's actually going to be an expression, which is fine. This one here, as p approach 0, that literally means plug in 0 everywhere you see a p. When you do that, what happens to this term? When you plug in 0? It goes away. When you plug in 0 here, what happens? It goes away. So the limit as p approaches 0 of this function is actually going to be what? 3x squared. Good stuff. Now this last one. We can do straight, plugging in, okay? If I plug in 0 for h, because I'm evaluating the limit as h approaches 0. If I plug in 0, I'll get x squared minus 6. What should I do with this right here? Distribute the negative, yeah. So that's going to be a minus x squared plus 6 all over h. What's 0? H is 0. What does the top turn into? 0 as well. Now the reason why I wanted to show you guys this is because if you do it algebraically and you end up with 0 over 0, that actually means that you can simplify your original function and try again. Okay? So if you get 0 over 0 whenever you're doing like the direct substituting in method and you get 0 over 0, that means you can simplify your original function and then try again. So let's simplify this. X plus h squared means to do what? Boil. So you have to do x plus h times x plus h. What is that? X squared xh plus xh, which is basically 2xh plus h squared. Minus 6, and I'm going to distribute the negative over again. And because I am simplifying this limit, I want to make sure that I include the notation to go along with it. A lot of students, you may be asked to do something like this on the IB exam, and if you don't include that notation out front, this limit part, then you're gonna get it wrong. Every step. All right. If you ever have to show something, we'll make sure you include it for every single step. Okay. This can simplify. The x squares do what? And the 6's do what? Cancel. So I'm left with the limit as h approaches 0 of 2xh plus h squared all over h. What do you notice? The h's cancel, but you gotta be careful. And I want to harp on this now versus later. If you ever have to show anything, show the fact that why are you canceling out an h? Okay, everything does have an h. So if you look at the top, if they have something in common, you usually do what to it?
Oh, you take it out.
You factor it out. And so I want to kind of harp on this now. If you ever have to show something and you're like, oh, and everything has something in common, I can cancel it out. Show the actual factor out part before you go to canceling out anything. Okay? And then you can cancel it out, yeah. So now we'll have the limit as h approaches 0 of 2x plus h. You can't really simplify any more from there. But now this time, when we plug in 0 for h, what do we get? And that's your answer. So, a lot of these problems can be done algebraically. Just real quick, to go back a little bit, all these could have been done algebraically. Clearly, when you found that it was 4, you could have been like, oh yeah, well 2 squared is just 4, right? Of course, because a quadratic is a continuous function. There are no gaps or holes or breaks in the quadratic, so of course, yes, plug it in, you get a 4. But when you plug in 1 for this one, what's 1 squared minus 1? What's 1 minus 1? 0 over 0 means what? Can we simplify? How can you simplify this? Perfect squares. The top can factor to what? X plus 1 and x minus 1. And these cancel out. So you're just left with an x plus 1. When you go to plug in 1, what's 1 plus 1? There you go. I'm not really going to talk about C because clearly you should have known that, hey, they're horizontal lines, so they're going to be approaching straight to these two opposite numbers. They're not even the same. But if you look at this one, into the piecewise function, if I plug in 2 into the top, what do I get? 5. When I plug in 2 into the bottom, what do I get? And clearly, if those numbers aren't the same, then the limit cannot exist. All right? Now, the one for sine x over x, when we actually get to a little bit more work with derivatives and trig functions, I might revisit this problem. But in this particular case, when you plug in 0, right, you'll have sine 0 over 0. What's the sine of 0? In the circle? 0. You have 0, 0, which means that that function can be simplified. There is a way to simplify this, but if I tell you this now, you'll be like, what is that? So I'll revisit it once we get a little further into this calculus unit. Okay? So I want you guys to go grab some whiteboards. We're going to do a little bit of practice. All right, so we're going to basically take this idea of a limit and how to go about evaluating for a function as it approaches a particular number, and we're going to apply it to the fundamental principle of calculus. Now, if you were asked to find the slope of this line, how would you do that? How would you find the slope of this line? Rise over run, right? That is what the slope is. But if I gave you 2 coordinates that represented the endpoints of this guy's walk, let's say this was 2, 1, and this was 6, 9, what would you do then? This forms the length.
geometry. I don't remember how to do it.
Flashback.
X1 minus X2. Oh, I thought it was 9 minus 1 over 6.
Wait, just kidding.
Oh, yeah, the slope one.
Y2 minus Y1 over X2 minus X1. Because rise is your Y's and run are your X's. So your Y's have to be on top of your X's.
I said 9 minus 1 over 6. Man, this is like algebra 1.
Yes, this is the old school slope formula. That's because we're dealing with a line, okay? A straight line. Alright? But to find the slope of this curve, okay? If you think about it, on a curve you have all types of different, it changes, okay? These are not straight lines, okay? There are definitely many when you're looking at a curve, okay? But calculus allows you to actually find the slope of this curve. Now, when you look at these lines here, okay? These lines that have these different points on them, okay? Every single one of these lines is touching the curve at one particular point. These lines will be called what? What are the names of the lines that touch something at exactly one point? Intersect has like a particular name. It does start with a T though. Say it.
Tangent?
Tangent. Every single one of these lines are tangents. Okay? They're tangent at those respective points. A, B, C. Okay? Hold on, stop writing. Stay with me, okay? This is where I lost last period, okay? Each one of those lines are tangent at those respective points, okay? Therefore, by finding the slope of those tangent lines, okay, that will actually give us the slope of the curve at that particular point, okay? So when you're looking at a curve, all right, you are going to be asked basically to find the slope of a curve at a particular point. In order to do that, what you're actually going to do is you're going to find the slope of those tangent lines at those respective points, okay? Now, if you think about like a quadratic, right? A quadratic goes on and on forever. It continues to get bigger, increases into infinity, okay? So you're not going to actually find like the slope of every single possible point that's on that quadratic, okay? However, you could find a rule, aka a function, all right, that actually gives us the slope at any point on any curve, okay? That's what we're actually going to be doing more likely, okay? We're going to be finding rules, aka functions, equations, that will help us find slopes at respective points. Now, slope, also known as the gradient, okay, gradient means slope basically, of a line or of a curve at a particular point is the measure of how fast y is changing as x changes. That's what slope is, okay? When you're doing rise or run, how fast are you going up? How fast are you running over? That's basically what you're doing. You're figuring out how fast the y's are changing in comparison to the x's. All right? Now, the most precise way to find the slope of these tangent lines is basically making secant lines and applying the limit process. Okay? So stay with me. Take a look at this picture right here. All right? This very first picture, it shows a curve and it shows a secant line. Now, secant is different from a tangent. A secant cuts a circle, a curve at two different points. Okay? As you can see, this is the point x, f of x. This is the point x plus h, f of x plus h. Okay? Basically 2 points. All right? Now, if we wanted to apply old school slope, we would do y2 minus y1 all over x2 minus x1, correct? That's what this part is right here. Okay, so the slope of the secant line is this. Okay? Now, by applying the limit process, and most specifically, the limit as h approaches 0. Okay? As h approaches 0, that means that h is basically getting smaller. Okay? As you can see in the second picture. All right? It's still a secant line, but h has clearly gotten smaller from picture 1 to picture 2. Wouldn't you agree? Okay?
Excuse me, teachers, pardon interruption.
And as h continues to get smaller, okay, if I bring this in, okay, basically h is approaching 0. basically to where it's no more, it's getting smaller and smaller, you will essentially get a tangent, okay? Because once h is finally at 0, you are going to have that tangent line. It's only going to cross the curve at exactly 1 point. No more at 2 points, but at 1 point. So evaluating the limit as h approaches 0 of your secant line allows you to do just that. It allows you to find the slope of your tangent line. Now this is known as the difference quotient. And it is also known as the formal definition of a derivative. Okay? Now some of the questions that I got last class were, a student that was confused, realize you're going to be given a function. Okay? You are going to be given a function. And so to actually figure out the slope of the tangent line at a particular point of the function that's given to you, you're going to plug in x plus h into that function. Simplify that. Then whatever you get from there, you're going to subtract it from the actual function itself and then divide by h and basically do what you've been doing. Okay, what we did on the whiteboards, what you did in the notes earlier. Yes?
So just to make sure then, so h is approaching, you're evaluating the limit at h approaches 0 because that's like the bottom, the leftmost point on the triangle.
Well, it's basically showing this part right here. H is that distance from this point to this point horizontally. So as h gets smaller and smaller, it's basically turning from a secant line into a tangent line.
Okay, so it's just isolating one of the 2 points on the secant line.
Mm-hmm.
Okay.
All right. So let's do that. We're going to find a rule for the function x squared minus 1, and then we're going to find the slope of the curve at 2 different points on this function. This function is a what? Quadratic. Okay? So to find the rule, okay, this is going to allow us to find any point at any point on the curve. We're going to use the limit process. The limit as h approaches 0, and yes, we're going to write that on every line going down. Now, you guys have access to see the formula right there on the page, correct? So I'm not going to rewrite it. But it says f of x plus h. That goes way back to like algebra 1, algebra 2, when you actually when it said f of whatever, you usually plugged it in for every x, correct? Same concept. You're plugging in x plus h for every x that you see. That's the first part of the formula. This right here is the f of x plus h part. Then it says minus f of x, correct? F of x is the original function, x squared plus 1. Now I'm including that inside of parentheses because I am subtracting the entire function, which means what am I going to do to that minus to this function? Distribute it. And a lot of students forget that, and then they end up with something that doesn't work out. All of this is over h. So we apply the formal definition, and then we simplify from here, okay? So the limit, as h approaches 0, we gotta FOIL this out. X plus h squared, and after a while, you're gonna know what x plus h squared is like that, because you're gonna do it so much. What is it? Yeah, I combined the two xh's. Okay? I still have the plus 1. And now, like you guys said, I want to distribute the negative. So minus x squared minus 1 all over h. Now, what do you see? How can I simplify this? X squared cancels out, 1's cancel out, and so I'm basically left with every term that has an h in it. And if you do this correctly, that should happen to you. Okay? Once you get to this point and you cross things out, you should only be left with the terms that have h's in them. If you end up with a term that still has it's just like 3x, no h, you did something wrong. Okay? That should let you know to go back. Maybe I squared x and h and I didn't FOIL it. Okay? Now from this point, what can we do? Factor out that h. Very good. So you'll have h parentheses 2x plus h all over. What can I do from here? Cross out the h's, so I'm going to be left with the 2x plus h. And now, plug in 0. When I plug in 0, what am I left with? 2x. 2x is the rule to help us find the slope at any point along this particular quadratic. That is the rule. Okay? Now we're going to use that rule to find the exact slope of the curves at these respective points. So when x equals 0, what is going to be the slope at that point? 0. When I plug in 1, what's going to be the slope when x is 1? 2. So this is basically saying by plugging in 0 and by plugging in 1, we're basically saying that the slope of the tangent line at 0 is going to have a slope of 0, so it's going to be a horizontal line. And then the slope at when x is 1, the tangent line is going to have a slope of 2. Take a look. Here's the picture. The blue represents the quadratic x squared plus 1. When x is 0, look at that tangent line. Isn't that tangent line horizontal? What's the slope of any horizontal line? 0. So we did good. Okay? Here's when x is 1. There's the tangent line that you guys see on your picture. Now, we can use old school slope to figure out, hey, to go from this point to this point on our tangent line, don't I go up 2 units and over 1 unit? What's that? 2. You found it. So the rule of 2x allowed us to find the slope at 0, at 1, and we could use to find the slope at 2 and at any other point. Questions? All right. So we're able to derive another function using the limit process. With this function, we're able to find the slope at any point on that function, okay? That's what we did. Now, this derived function is called the derivative. This function is called the derivative. Now, the notation to represent derivative is usually f prime of x. It's an apostrophe. It's not a 1. It's like an apostrophe, okay? But it's read f prime of x. The process of finding the derivative is called differentiation. So, you may ask, like, it may say differentiate. That just means find the derivative. To find the derivative, you evaluate the limit as h approaches 0 of f of x plus h and so on and so forth. That's basically what you're doing. All right? When you find the derivative, when you find that formula, okay, you're finding the formula for the instantaneous rate of change of a function. Okay? There's two different things. There's instantaneous rate of change, and then there's average rate of change. Average rate of change would have been done in pre-cal. That's when you use old school slope. That's when you do y2 minus y1 over x2 minus x1. But instantaneous rate of change is when you actually do the derivative. That finds it at a particular point. Okay? Questions? You do slope. Yeah. Because basically what you're finding is, it's basically like you're finding the slope of the secant line when you do average rate of change. But when you do instantaneous, it's like you're finding the slope of the tangent line at that particular point. Exactly. Now, some other notations for derivative are what you see up here on the board. And it really kind of just depends on how the original function is given to you. If the original function is given to you as f of x and they ask you to differentiate, find the derivative, then yes, of course you're going to use f prime of x. That's the notation for it. But if they give you y, instead like y equals x squared, then when you write the derivative, you use y prime equals. You see what I mean? Dy dx also goes with y. Okay? And this one down at the bottom, this was actually like the first way they represented derivative notation when it was first discovered. Okay, this is a very, the last one's a very classic way to do it. Okay, so the older calculus textbooks will have this notation, but the newer calculus will have the top two and then the one from the other page. But I don't want you to be confused if you saw any. See, I'll make derivative, which means do the limit process. So, we're going to practice. We're going to find the derivative, i.e. apply the difference quotient to this function here. Do you guys want to do this one together or on your own? Do it together? Okay. Do the one we do together, but the rest you do it on your own. Alright? So the limit as h approaches 0. Of course, we start out with that. Now we have f of x plus h. That means we're going to plug in an x plus h everywhere we see an x. So just a heads up, if there are multiple x's in your original function, you got to plug in x plus h into each one. Okay? Then we subtract f of x. And all of this is over h. I am still recording. So now x plus h cubed. I'm going to let you guys work that out and then we'll come back together.
I don't even know if the factor is.
Yeah. So when you boil it, you should end up with x cubed plus 3x squared h plus 3x h squared plus h cubed. Did you guys get that when you did?
It was a 3. I got 4.
Yeah, I put 2. Yeah.
How did you get 4?
Alright, so from here, we can see some things should cancel out, and it should be everything that doesn't have an h. So that's x cubed and negative x cubed. So we're left with 3x squared h plus 3x h squared plus h cubed all over h. Yeah? We can factor out an h. That's 3x squared plus 3x h plus h squared all over h. The h's cancel out. So you're left with 3x squared plus 3xh plus h squared. Now at this point we can't go any further. So when we actually plug in 0, what are we left with? 3x squared. So the derivative using the notation of f prime of x is going to be equal to 3x squared. Because we are finding the derivative now, not the actual limit. So we're going to use the notation for derivative, and that's where 3x squared comes from. All right. So now after you boil, distributed, yeah?
Yeah.
So then you're only left with 6x plus 3h squared plus 2h over h. Now if you're crossing out things that don't have h's, they gotta like match up. Unless you might have messed up somewhere else. So then take out an h. Cancel out. And evaluate the limit as h approaches 0, which leaves you with the derivative of y prime, which is 6x plus 2. Who got that? Good stuff. All right, do the next one.